Hello, everyone. This is the Cooperative Communication Network's lectures for the summer semester. Today's talk is about the technology-enabled cooperation, and we are tackling the first lecture of compressed sensing. I am Marwa Tarouti, a PhD researcher at the Deutsche Telekom Chair of Communication Networks. And the outline of my talk would be first, we would like to understand the problem of compressed sensing from different angles. And then um, we understand or explain what is sparsity, what is the relationship between sparsity and compressibility. Then we move to what we call sparse representation. And then we move to how we actually build or design the measurement matrix. Then we move to discuss some basic algorithms that we use for signal recovery for the compressed sensing problem. And then we will be finishing by giving a nice example about the orthogonal matching pursuit that I haven't personally made myself, but I found it online while I was still learning about compressed sensing, and I really, really appreciate and understanding the OMP algorithm. That's why I wanted to include it here, and I want everybody to enjoy understanding this algorithm because it's going to be useful for us, especially in the next lecture, as well as the part of the ComNet's book, chapter 22, which is basically related to having a framework where we are playing around with compressed sensing uh, with data that are collected from some sensors. Okay, so let's start by given a contemporary paradox. You could see here we have two pictures. One is a raw representation of some nice spring flower. Uh, the raw image size is 15 megabyte, whereas when we use a JPEG compression, we would see that this will be reduced to only 150 kilobytes. We can notice that basically for our eyes, we don't see any differences between both pictures. So then we could think that maybe we are actually having a massive data acquisition where most of the data is actually redundant. Therefore, we can actually withdraw it, and in this case, we can get rid of this enormous wasteful data that we are collecting while taking pictures or and so on and so forth. So now we would start by understanding what is this compressed sensing, how can we think about it, or how can we analytically see it. So we are moving from these images into projecting this into a simple analytical problem where the JPEG image is simply denoted as a small vector y, which is nothing but the projection of the large vector x, which is the raw image to begin with, into into a certain using a certain matrix A. So here we will have the sorry. So here we have y equals ax. X is a large um, vector of size n. Y is way smaller vector, and we have our Sensen matrix A of dimensions m times n. So here the task is to recover x, knowing that we do not have exactly as many and at least as many unknowns as the equations, because that's what we usually have seen or have learned in traditional or standard linear algebra. Here we are having a different problem. We have an underdetermined system of equations that is actually breaking with this main theorem of algebra. So here we see that we are actually having an incomplete information then somebody would ask, like, can I even reconstruct the original data or original signal having only y and a, and both dimensions are um, far smaller than my original signal? If we want to think about this problem as simple as it is algebraically, then we can end up having an infinite number of solutions. But that's actually not what we want to. We want to find a specific solution for this. There is no magic, of course. We are not doing witchcraft here. Therefore, we need to impose some certain constraints to have an efficient recovery. And then the other question would be how to get an estimation of this signal, because sometimes the reconstruction cannot be 100% accurate. So therefore, we want to call it an estimation of our signal X from exactly M measurements. Additionally, we've seen also um, the Shannon-Nyquist sampling theorem that we studied some time ago in university, and we all have kept in mind, we kept saying, like, there is no way that an information could be lost if we sample at a rate that is twice the bandwidth. So this limitation cannot go along with what I just discussed in the previous slide. And the compressed sensing came to break with the barrier of the Shannon-Nyquist theorem, and it states that the sampling rate can be highly reduced as soon as a specific a priori knowledge about the signal structure is actually available. So precisely the people who were interested or who um, founded the field or the theory of compressed sensing, they were saying that if the signal of interest has a sparse or at least a compressible, and we will talk about compressibility a little bit further. So if you have a signal that has a sparse representation in a certain base or certain frames, then we are we are able to have a compressed sensing problem, and we are no longer limited by the signal structure. Sorry, we are no longer limited by the bandwidth of that we have, but we are actually limited by the signal structure. So here we are breaking the Shannon-Nyquist barrier. I would like to maybe point those who are a little bit mathematically curious to understand a little bit more about bases and frames to read about in chapter 10 of the Comnet's book. I personally have put some nice definitions there that you could get the difference between both of them. Okay, so now that we've seen that we are defining the standard linear algebra um, statements. We are breaking with the Shannon-Nyquist theorem. We have to think in a way how to really solve this problem. Obviously, we have to write it in a way that is an optimization problem at the end. So here, what we want to do, we would like to minimize x, or finding the sparsest solution x, subject to the equation presented a bit earlier, subject to y equals ax. So the theory asserts that a signal x could be recovered from a far few simples or measurements. Here they are y. So maybe it's easier to get used to saying measurements rather than samples, because that's what we say in the compressed sensing field. So we are able to recover it from far few measurements, where m is actually extremely small compared to n. Yeah. So finding an efficient solution for this problem relies on two main important components. The first one is that the signal has to be sparse, or at least has to have a sparse representation somewhere using a basis or a frame. We will discuss a little bit these in details within this lecture and the next one. So we need to have a signal sparsity. Here, it should be k, why of course k is relatively small compared to n, and should also be smaller than m. And then we have to verify one of these properties that our sensing matrix should obey to make sure the process of compressed sensing is actually feasible. So amongst these properties, in this lecture, we will be focusing on the coherence and the restricted isometry property, the RIP, and we will see a little bit further how to design a matrix using these two properties and why we need them. So what are we going to expect when we hear the word compressed sensing? What can we think of it? So the compressed sensing promised to provide a disruptive approach for data acquisition. So we are overcoming the common wisdom, which is the Nyquist theory from one side and the linear algebra on the other side, both combined. And compressed sensing assures that exact reconstruction of sparse signals from a small number of measurements is actually feasible. So before going further, um, maybe some of you have seen these before. I'm pretty sure even in high school you have seen these, but maybe they look a little bit different now. Okay, so we would like to understand what are these norms, and as simple as it is. So we define an LP norm of a vector, a certain vector x in a Rn as the norm p, which is the sum of all absolute values power p. All of this is power 1 over p. I'm so sorry, it's a bit tough to explain this in English, but I hope everybody can see it and I understand it. I'm sorry for that. I haven't studied the math in English, so it's a bit tough for me to explain it, but let's get a little bit further. So here, the norm, so here the norm is only valid, we can say a norm, when only our p is actually between 1 and the infinity. Of course, we have an infinity norm, and that we can talk about norms as long as we are able to satisfy a p triangle inequality. As you see, the sum of two vectors like normed in p norm power p, it should be smaller or equal to the separate sum of the norm p of x power p and the norm y the norm p of y power p. So we can take a simple example that, sorry, all of you know. So let's go to the normal coordinate system. Let's say we know where we have x equals x1 and x2. You could see in the figure below that here we are representing x1 and here x2. And if we have if we want to represent the L 1 over 2 norm, we will have the following. And if we are trying to represent the P1 norm, we get the dime, and then P2 and P infinity. So, for example, P1 is nothing than the sum of absolute values of our signal of interest or vector of interest, whereas the P2 norm is the Euclidean norm that we all know. Okay, So earlier we said that we can only talk about a norm if our p is actually larger or equal than 1, which makes the L 1 over 2 norm as a it's actually not a norm. And for all p's that are between 0 and 1, the notion of a norm is actually lost. That's why I put a quotation no sorry quotation marks between norm when I mentioned the L0. But for those who are curious about literature, maybe you will see a lot of papers or works that simply abusively use the term L0 norm for the L0 representation, or maybe more accurately, we could call it pseudo norm. So if I want to go and understand this L0, let's say norm, um, it is no different than the other representation, except that here we will end up having imagine that your xy's are all over zeros, except somewhere you have an zero 0.5, let's say, and then you need the absolute value power 0. This gives me a 1. So basically here what I'm actually calculating is I'm going through the vector element by element and checking. If that element is 0, then it's discarded. If that element is not 0, then I'm incrementing uh, uh, a certain variable here, the L0 by 1. So in overall, this L0 representation would be nothing than the support of a vector. While support of a vector is exactly the number of non-zero element of inside a vector. Sorry, not the number, gives the locations of the non-zero elements within a vector. So if we go and calculate the cardinality of all these positions, we will end up having the number of non-zero elements of the vector. And this is done based on the support, yeah, exactly, which gives the exact location of non-zero elements. Okay, and you could see that it's actually quite different from the other norms that we have discussed. Okay, so back to our optimization problem that we mentioned earlier. We would like to find the sparsest solution x subject to y equals ax. And the task here is to find the number of non-zero entries in X. And of course, if I know how many zeros that I don't have, sorry, how many non-zero elements that I have, I can easily find what are these non-zero elements. Because here the problem is not finding, writing down the solution, but where is the solution, like where the non-zero elements within the vector are actually placed. Sorry. So let us call a sigma kn, which is the set that contains all k-sparse vectors in Rn, and you could see the definition mathematically below. And yeah, so if X is actually k-sparse, then it must belong to one of these subspaces in Rn. But it's not an easy task to just find this solution. It actually requires a very exhaustive search through all these subsets that we have in order to find to which subspace actually X belongs. And this is a combinatorial problem that can cause like a computation problems if we want to bring the compressed sensing in some applications. So here is the essence of the idea of compressed sensing, because what we said before is existent since forever, but there was the Professor Candace who at some point in 2004-5 um, showed or proved that we can actually move from L0 norm to L1 norm, and we can actually, and this L1 norm could help us to find the solution for our compressed sensing problem and gives the exact solution as if it was really done using the L0. Okay, so we said that this L0 minimization um, is actually an NP hard, so it is not practical. We don't want to do it. And the from the main proposal by the Professor Candice, it says that L1 norm is actually equivalent to L0 in a technical sense. So this enables us to move a little bit further using the L1 norm. So a good approximation is to use a solution to the corresponding L1 optimization problem by finding the values of all the coefficients where x1 is the smallest possible. Okay, until here seems okay, okay. And there was a very old algorithm called the basis pursuit, which is an L1 minimization strategy that has been used for solving usually convex optimization problems in the form of mean um, the sum of absolute values of x subject to y equals ax. Okay, so we had a non-convex optimization problem that we magically converted into a convex optimization problem. Seems actually good. This is how compressed sensing era has started. It is less problematic than the working using the support of a vector. It is promising, but still it relies on linear programming because basis pursuit is a linear program at the end, and this method do not have strong polynomially bounded runtimes. Means it will slow down your software. It will also require some time to run and to find the solution. So it is not so good, but it is not as bad as the L0. Therefore, we are seeking other alternatives. So before moving forward, I would like to summarize in a nutshell what we want to do with when we have a problem that seems to be a compressed sensing problem. So here we want to recover a signal x of size n from far few samples or measurements of size m, where m is really small, and it could be approximated um, by an OK log n if x actually admits a k-sparse representation in some orthonormal basis psi. Because in some cases, actually, we don't really see the sparsity. So if I'm talking about a temperature reading within a day, we could see that, for example, if today is 18 degrees, then in this hour 18, next hour 18, 18, might have a few jumps at the to 19, maybe fluctuates to 15 and so on, but most of the values would be 18. We don't see zeros here, but you can just understand that like in a very basic calculation, we could feel that there is actually sparsity here. But in a more complex situations where we don't have easy values like what I just mentioned, we are actually trying to find a representation that is sparse in another basis. So we are projecting our signal into an orthonormal basis or maybe a frame that is psi, and psi of course has the same size the dimension of psi is n by n. It is called a transform matrix, where by projecting x, we can find a sparse representation for it. And our alpha is the sparse representation of x. So here the sparsity is actually seen clearly in alpha. And of course, A is what we call the measurement matrix, which remains as we have seen before. Now the task will be updated. And now we are trying to find the sparsest alpha for this optimization problem. And then easy peasy, we can get back to our X. So these measurements, the Y, they are actually non-adaptive. They are independent. They don't, there is no causality here. Mm, They are not supposed to match the signal structure at all. They are extremely random to the point that like the more noisy they look like, the better it is. So please do not be confused by the fact that we are seeing some multiplication between vectors and matrices. It's actually all done. It's all projections. This means we are using all over this lecture and the next one some inner products. So my first measurement is nothing but uh, projecting our signal or sparse vector x in the matrix A, and you could see like the simple inner product multiplication here. We have, we have a1 by x, we get a scalar, and then y2, we get another scalar thanks to this inner product, and so on and so forth, until we arrive to the very last row of the matrix A. So these measurements, they are like all of them equally important, funnily equally unimportant. So why they are important? Because like equally important, you feel like some kind of democracy. All of them, they're good, we need them, but if we are losing some of them, it will not affect the reconstruction. So maybe you have attended the network coding lectures, and this is a quite funny. It's a little bit different. For network coding, for example, you are not able to recover your packet at all if one or more of the coded packets haven't arrived. But here, if something is lost, we're like, okay, whatever, we will get an approximation. So there is always a chance for reconstruction. And that's why I would like to term it as a robust. So here we have a robustness, democracy, and the reconstruction or error, of course, it decreases at a near optimal rate as we increase the number of measurements. That's like an intuitive deduction. Okay, so now we move to understanding the sparsity of a signal and also compressibility. This term seems to be interesting because we hear compressed sensing. Okay, so the sparsity, um, it plays a very important role on how we can actually estimate signals in the presence of noise. Um, those who are mainly interested in the signal processing field, they will see that sparsity is like the best thing that you could have. Um, it gives good features to play around. You can perform some transform coding. You can also use it for solving inverse problems like the field of geophysics, some other stuff related to maybe studying the Earth and its geology. Also, the dimensionality reduction, it helps to facilitate the modeling. So we can have simpler algorithms. Here, our focus is on this sparsity, how it helps to determine how quickly we can acquire signals in a non-adaptive fashion. So the definition of sparsity is actually related to the support. We are we are trying to find a support of a vector x that is where the components are x1 until xn, and it is the index set of its non-zero entries. And you can see here in this example that most of the elements are zero except a few, 1, 2, 3, 4, 5, 6, 7, 8, if I'm not wrong. So here we have like the support is composed of 8 elements. The first one should be 5, the second should be 7, and so on and so forth. Get into the guessing the like the sparsity of the vector. We just need to find a cardinal or calculate the number of elements of the support set. Okay, and it is also nice to remember or put in mind that that sparsity is encountered in signals of enormous number of applications such as images, audio, and so on and so forth. However, in practice, the sparsity could become a strong constraint to impose. So we prefer to have a weaker concept of what we call compressibility. You could see at the bottom of the slide some example of a compressible signal where you could see that we have some elements that are really, really close to be zero, but they're actually not, whilst we have other elements that are their amplitude or their values are actually large. And this weaker concept helps us as in real world signals that are actually not exactly sparse, but they are rather compressible, and they can be well approximated by the sparse signals. So we may consider vectors that are nearly k-sparse as measured by the error of the best k-term approximation. Additionally, uh, here you could see another graph where we represent the absolute values of our signal x on the y-axis, whilst here we let's say put the index of the signal. So those sparse signals, if we sort their elements, you could see that we are having a set of non-zero elements, and at some point it sharply goes to zero from k to n. And for a compressible signal, so here we have the k term approximation, and you could see that maybe not all the elements they are zero, but most of them they tend to be zero. So that's basically the difference between both of the signals. Analytically, we could represent the compressibility using the following definition. For P, which is larger or equal than zero, the LP error of the best k-term approximation to a vector x is actually defined by sigma k of the signal x, with and P referring to the LP norm. And we follow this specific rule. So Candace mentioned in one of his papers that many natural signals are sparse or compressible in the sense that they have concise representations when expressed in the proper basis. This means that the signal in question could actually, there is a way to find a representation where it is actually sparse. But now the question is how to find this proper basis to represent the signal. So here we would like to exploit the concise nature of the, like we have natural signals, and here the perceptual loss is actually hardly noticeable. So now we move to the sparse representation part. So as we mentioned before that um, if we express the signal in a proper way, using a specific basis, then we can end up having our x like divided or separated into a matrix, a transform matrix psi, and the theta, or what I mentioned earlier, alpha. This might be must be a typo from me. So here we have, like, there is no magic. We cannot have vector x that can, like, out of a blank be transformed into another vector that is sparse. So, like, the information or the content of this specific vector, where did it go? Simply, it is not entirely put in the theta, but most of it could be expressed in what we call here the psi. Amongst the examples of very well known transforms, we remember the Fourier transform, where we have the when we where we go from the time to domain to the frequency domain, where we have these um, uh, like sinusoidal representations in the time domain, and then they become just spikes in the frequency domains. Also, the wavelet transform. We have also discrete cosine transform, Haar transform, Gabor filters, and many, many others. That those who are interested in, they can look into the internet to find some others. And actually, each of them uh, could be a good use for certain type of signals. So for here, for example, the DCT provides a very good representation for images, for example, ECG, humidity, temperature data, and so on and so forth. But it is also not straightforward to find the right transform for a specific, let's say, type of a data, sorry, or a type of data, or signals. And sometimes signals, they cannot admit a sparse representation using these well-known transform. So here we have a limitation, because there is like a limited number of transforms to keep trying to use. But there is also something really cool that you could actually get yourself. We call a dictionary, which is a generalization to transform. So these dictionaries, I mean, the name itself sounds like, okay, a dictionary. It contains a whole language. So the dictionary is a kind of a language, and your signal X. So here, let's pretend the dictionary is here actually psi. So my signal X is simply represented in the language psi, the dictionary, using certain elements. So basically, my theta is me picking certain words to use from that specific language or a dictionary. I'm not going to talk further about dictionaries in this talk, but in the future lecture, we will be go into details into understanding how to get how to have your own dictionary, how to design it, and how well it could approximate your data. Okay, so here we take an example using a wavelet transform. We have a picture that has 96 kilo incoherent measurements of a compressed sensing image. It is perfectly sparse, and it has 25K non-zero wavelet coefficients. And then we do our optimization technique to recover the image. You could notice that both images, they look, of course, alike to our eye, and The original image here to the left is actually reconstructed here after discarding exactly like 97.5% percent of the coefficients. So that is a lot of elements that were discarded.